We finished section 7.3 last time. We looked at exponential generating functions. Now let us look at linear homogeneous recurrence relations. 7.4 linear homogeneous GENOUS recurrence relations. Recurrence relations. So we know what recurrence relations means, right? Fibonacci sequence where you're referring to the nth term in terms of the n minus 1th term. This is called recurrence relation, stuff like that. What is a linear homogeneous recurrence relation? So given a sequence Hn, n is equal to 0 to infinity. Suppose it satisfies h of n is equal to a times h of n minus 1 plus b times h of n minus 2 plus c, where a, b, and c may depend on where a, b, and c may depend on n, may depend on n. For example, if n is even or n is odd, things might become different. Such a thing is called a linear recurrence relation. Okay, it's in terms of nothing is getting squared, there are no multiplications or anything, random multiplications. You're just giving them coefficients, and that is called a linear recurrence relation. So for example, Fibonacci sequence numbers or sequence satisfies fn is equal to f of n minus 1 plus f of n minus 2. Therefore, a is equal to b is equal to 1, c is equal to 0, right? And as we discussed before, it is important to write for Fibonacci numbers what f of 0 and f of 1 are. Another example that you have seen before that you perhaps might have forgotten are the derangement numbers. Derangement numbers. Dn. Right? We saw these derangement numbers Dn before, and they had Dn is equal to n minus 1 times Dn minus 1 plus Dn minus 2, but we are going to write it as n minus 1 times Dn minus 1 plus n minus 1 times Dn minus 2 for n greater than or equal to 2, with again d of 0 is equal to 1, d of 1 is equal to 0. So now these are shifted, right? And we had that again a is equal to b there, and it's n minus 1, and c is equal to 0. So you might have noticed in both of these cases I have my c is equal to 0, and if the c is 0, they are called homogeneous. Okay, so that's why I'm looking at linear homogeneous recurrence relations in the name. Oops. Linear homogeneous recurrence relations. Okay. There's another way of looking at the same thing. These numbers Dn are also n times Dn minus 1 plus negative 1 to the n. For n is greater than or equal to 0, n is greater than or equal to 1, and in that case, we just need d0 is equal to 1. And here my c is not equal to, so a is equal to n, b is equal to 0, and c is equal to -1 to the n, right? So first of all, it depends on n, and second of all, it's not 0. So this is an example of a non-homogeneous recurrence relation, okay? And so let me write it down. Special cases of linear recurrence relations. What are the special cases? In examples 1 and 2, we found that we saw A, B, C were independent of n. Independent of n, and in that case we call these as constant coefficient. Okay, in the third case, my c depends on on n. It is -1 to the n, right? So it is not constant coefficient. If my c is equal to 0, then as I mentioned before, this is called homogeneous. Homogeneous, whatever. Okay, so generally we will be looking at constant coefficients and homogeneous. So we are going to assume 1 and 2 for all our cases in this chapter. We won't be dealing with weird things. Okay. Example, we want to solve the recurrence relation h of n is equal to 3 h of n minus 1 plus 4 h of n minus 2 minus 12 h of n minus 3 for n greater than or equal to 3, with h of 0 is equal to 5, h of 1 is equal to -11, and h of 2 is equal to 15. Okay, so this is again, while it's not exactly ABC, this is again linear, right? Every term is multiplied by just a constant coefficient. They're not getting multiplied by anything of that sort, right? So the idea is you want to always do the following. Whenever you have such a thing, we did the same for Fibonacci, okay? We are going to do the same here. Take hn is equal to q to the n. Right? We did the exact same thing for Fibonacci sequence, and we are going to use the same technique to solve it. Okay, therefore q to the n is equal to 3 times q to the n minus 1 plus 4 times q to the n minus 2 minus 12 times q to the n minus 3, right? N greater than or equal to 3. And what I can do is either I can factor out q to the n minus 3 from everywhere, or I can just take n is equal to 3. Okay, therefore q cubed is equal to, let us assume that I factored out q to the n minus 3, and I am going to assume that q is not 0, because q being 0 would be a really dumb solution. Okay, so then I get this is 3q cubed, 3q squared plus 4q minus 12, and therefore q cubed minus 3q squared plus 4q minus 12 is equal to 0. Now this is a cubic polynomial. When we did for Fibonacci sequence, it was a nice quadratic polynomial. Here, life isn't as good, right? We are getting a cubic polynomial. So let us try to figure out the solutions for this. 1 is not a solution because 1 minus 3 plus 4 would be 2, minus 12 is 0. Is 2 a solution? 2 cube 8 minus 3 2s are 12 plus 4 2s are 8 minus 12. Oh, sorry, I messed up my signs. Minus, that's a, sorry, this should have been a minus and this should have been a plus. Okay, so if I plug in 2, it does indeed give me 0, and I can work it through it repeatedly, and I get q cubed minus 3q squared minus 4q plus 12 is equal to x minus 2 times x plus 2 times x minus 3. Okay, so we can factor this, and therefore I get my q has to be either 2, -2, or 3. Okay, and what does this mean? So I have 3 possible sequences that could be my answer. Solution 1, h of n is equal to 2 to the n, right? Because I said my h of n's were just q to the n, and I found values for q. Well, solution 2, h of n is equal to -2 to the n, and solution 3, h of n is equal to 3 to the n. Okay, great, but this does not completely solve my question, right? First of all, these are not the only solution. As we saw with Fibonacci sequence, any linear combination of these is a solution. Therefore, any linear combination of these is a solution, right? And so my general solution h of n is going to look like a times 2 to the n plus b times -2 to the n plus c times 3 to the n. Okay, and now I say that, oh, any solution, claim any solution of, let me mark this maybe as star. So any solution of star looks like this. Looks like a times 2 to the n plus b times -2 to the n plus c times 3 to the n. 3 to the n. Okay, and here's how we do it. Proof. Well, consider a solution h1, h2, h3. Consider there are more than one solutions. Okay, suppose there are infinitely many solutions. I don't know how many solutions are there. Suppose a solution is hn n is equal to 0 to infinity. Okay, then consider h of 0, h of 1, and h of 2, right? Then solve a plus b plus c is equal to h of 0, 2a minus 2b plus 3c is equal to h of 1, and 2 squared a minus plus negative 2 squared b plus 3 squared c is equal to h2. Okay, solve this for a, b, and ABC. Okay, and use these a, b, c to define h of n is equal to a times 2 to the n plus b times negative 2 to the n plus c times 3 to the n. Now, it might be slightly hard to figure out these a, b, and c, but it is always possible to do so. Okay, as long as these equations are linearly independent, as in one is not a multiplication or the addition of the first two, right? We can always find such a, b, and c. And then what we get is then hn is a solution of star small hn is a solution of star and h0 is equal to h0 is equal to small h0, h1 is equal to small h1, h2 is equal to small h2, right? But if both of them solve the same exact equation and everything is defined by h0, h1, and h2, either of them, then therefore hn is equal to small hn for every n greater than or equal to 0. So as long as you can solve these equations right here, you can always find a solution in this form, right? Now solving these equations can be painful, right? So generally I'll give you, if I'm giving you questions, they'll be easier, but otherwise you'll have to slightly work them out. Okay, so in going back to our previous example, in our example we have h of n was equal to h of 0 was equal to 5, h of 1 was equal to negative 11, and h of 2 was equal to 15, right? And so I therefore want a plus b plus c is equal to 5, 2a minus 2b plus 3c is equal to negative 11, and 4a plus 4b plus 9c is equal to 15. Okay, now I hope you guys are able to solve this system of linear equations. For this specific one, I am going to show you how to do it in case you have forgotten and need a refresher. Solve. So I am going to call this equation A, B, and C. So C minus 4A is going to be 4 times A is 4A plus 4B plus 4C. C minus 4A is going to be 9C minus 4C is equal to 5C. And that is going to be 20 minus, let me do this, let me just do it completely. 4A plus 4B plus 4C plus 9C, my bad. 9C minus 4A plus 4B plus 4C is equal to 15 minus 20. Therefore, 5C is equal to negative 5. Therefore, C is equal to negative 1. Great, I have already found the value of C, and therefore I get A plus B is equal to 6, and 2A minus 2B is equal to negative 11 plus 3, which is negative 8. Therefore, so let me call this maybe D and E, whatever. 2D plus E gives me 2A plus 2B plus 2A minus 2B is equal to 6 minus 8. Can I make a mistake somewhere? Therefore, therefore 4A is equal to negative 2. Therefore, A is equal to negative 1/2. And so I get, therefore, putting this back in D, B is equal to positive 5.5. Oh, that's where the mistake is. My bad. Okay. I knew I was making a mistake somewhere. Okay, my bad. This should have been a, oops. This should have been a 12. Yeah, such mistakes can happen, which is why it's good to work it out and plug them back in. Okay, therefore 4A is equal to 4, and therefore A is equal to 1, and therefore B is equal to, well, 1 plus 5 is equal to 6, so B is equal to 5, right? And therefore my very specific solution to this case, therefore h of n is equal to 2 to the n plus 5 times negative 2 to the n minus 3 to the n for n greater than or equal to 0. Okay, so that's this is the end of chapter section 7.4. This is the exact same method you'd have to use for every single problem. Every single problem is going to essentially come down to having to solve for these 3 equations right here. Not exactly 2, B, and C, but whatever. Where did it go? Yeah, so solving such equations, And the technique for solving such equations is what I did here. Find the proper things, eliminate things, find value of one of the variables, plug it in another. Things could be slightly more complicated in a general problem, okay? But the idea stays the same.